Hello and welcome to this video. This video is a recap of what we have just discussed in our online lecture. In the online lecture, we discussed the topic on waves and we concentrated on two main points. The first one was definition of a wave. We wanted to know if somebody asked you, what is a wave? What would you say? And then we went through the properties that are common to all types of waves. So this being a recap, I just want to go straight to the point. And the first one was the definition of a wave. A wave is any disturbance in a medium which is used to transport energy or which results in transportation of energy or movement of energy from one point, which is referred to as the source, to the surrounding region. So remember that. A wave is a disturbance in a medium. And this disturbance is used to transport energy from one point to another point in the same medium. And then we were confronted with a situation whereby we wanted to look at what are the properties which are common to all types of waves. And in order to do that, we considered three systems. The first one is a simple pendulum. A simple pendulum consists of a small mass tied to a piece of thread, and then it is suspended on a support. And then the mass is displaced sideways and then allowed to swing. But maybe I would start with one which looks like the type of wave which we have in mind. And this is wave in a string. And this is what we have. We have a string over here, and we could move this string up and down. So I'm going to set it into oscillation. Like that. I can allow one point to move up and down, just like you would do with any other rope out there. That is the kind of wave that you're going to generate. Let me slow it down so that we can see exactly what we discussed. Let me hold this ruler just next to the green particle here. You can see that that green particle is moving to and fro about this rest position. And of course, I want to freeze the motion so that now we can say the maximum displacement of this particle from equilibrium position is referred to as amplitude of the wave. So that is the first point that you wrote down when it comes to properties of waves. Number one, amplitude. Amplitude is the maximum displacement of the particle from its rest position. And over here, we are able to identify particles that have achieved this maximum displacement. It will be this particle here, this amount of displacement, and we can actually pick a ruler and be able to measure that over there. Another particle that has achieved the maximum displacement is exactly this one, the green particle over there. Now displacement can either be positive or negative. There is another particle that has achieved a negative displacement here. That is how we identified, or you would be expected to identify, amplitude on a wave. Let's look at another system. This other system was one of the simple pendulum. This simple pendulum, it always starts from some point there, and then I would displace it from its equilibrium position. Also observe there is an equilibrium position here, and I'm displacing that mass from the equilibrium position. And then when I release it, it starts executing oscillations. Again, that maximum displacement of the particle from its equilibrium position is what we refer to as the amplitude of the oscillation. And of course, the last part was where we considered mass on a spring. I can attach this mass to this spring and then allow it to execute oscillations. At this particular moment, I would put the equilibrium position, which will be represented by this dotted line, and you can see actually this end of the spring is moving to and fro about that particular point. And again, you can see all these systems have got particles which are moving. It's either the mass of the simple pendulum, the mass on a spring or suspended from a spring, or the end of the rope which is moving to and fro about an equilibrium position. So that maximum displacement of the particle from its equilibrium position is called amplitude. That is the next important statement that you write down. So two statements: definition of a wave, and the next one is properties of waves. Number one, amplitude. Let's look at a physical property we refer to as periodic time. And in order to do that, we are going to revert back to the simple pendulum, periodic time. In order to do that, let's try to see what is meant by a complete oscillation. So I'm going to have this pendulum as it swings, and of course I'm going to slow down the motion because I don't want it to move so fast, so that you can be able to see what it traces. So let me start the mass. So it starts tracing that path. That is the first quarter, the second quarter, the third quarter, and then the fourth quarter. It comes back to that point and it completes an oscillation. So a complete oscillation has 4 quarters. And each one of those quarters is represented by a displacement equal to the amplitude. So if the amplitude, for example, is 3 centimeters, it will move like this. There will be the first 3 centimeters, then plus another 3 centimeters making 6, plus another 3 centimeters making 9, and then the last 3 centimeters making 12. When we consider that kind of motion, there are 2 physical quantities or properties of waves that we can define from here. One of them is the periodic time. The time it takes for this particle to complete an oscillation is referred to as the periodic time. And of course, we can measure that periodic time using a stopwatch. You can get this stopwatch here, put it over here, so that as soon as it crosses, let us wait for it to come back, repeating that oscillation, and then we get the time for one complete oscillation. So probably now when it is coming back, as soon as it crosses that point, I start the stop clock. It's running. That's the second quarter, the third quarter, and at the count of the fourth quarter, there I stop the stop clock, and you can see that the periodic time is about 1.7 seconds. So remember, the second property of waves is periodic time. Periodic time is defined as the time taken for the particle to make one oscillation or one vibration. The next property is referred to as wavelength. So you will remember that we have just said that the amplitude is 3 centimeters. And you can see that in a complete cycle, that particle moves through a total distance of 12 centimeters. 3 plus 3 plus 3 plus 3. 12 centimeters. The total distance covered by the particle when the particle makes one complete oscillation is referred to as wavelength. That is the third property of waves. The next property of waves is referred to as frequency. Frequency. When I have this particle oscillating, let's now have it oscillating normally. This time, I don't want it to trace the path like that. And you can see I can get the number of oscillations that it makes in 1 second. Let me increase the frequency. by maybe doing this experiment on a different planet with a higher value of gravitational field strength, such as Jupiter. And you can see on that planet, the mass is going to oscillate much faster. It's going to make many oscillations per unit time. The physical quantity that we are talking about here is referred to as frequency. Frequency is the number of oscillations that particle makes per unit time. And the frequency is measured in hertz. By the way, when I go back to amplitude, because it's a distance, it's measured in meters. When I come to wavelength, it's also a distance, it's measured in meters. When I come to periodic time, it is measured in seconds. Now frequency is measured in units we call hertz or per second. I'm going to illustrate that one in a minute. So those are 4 properties of waves. Let's look at the final property, which is referred to as the speed of the wave. In order to do this, we are going to combine 2 other physical quantities. Observe that the first 4 or 3 physical quantities are actually measured directly. We measure the amplitude, we measure the wavelength, we measure the periodic time, and then we can calculate the frequency. But we can also measure it in 1 second, how many oscillations are made over here. So let's go here where we are going to see how we can calculate the speed of the wave. Now over here, this is the slide that we used. If you're in that class, you remember that this is how we inked this slide. So I started by defining that 5th property of the wave, which is speed. Speed of a wave is the distance that the wave covers in unit time. And the equation that is used to calculate speed, or the equation which is associated with the definition of speed is equal to distance over time. In other words, you get the distance that the wave has covered, you divide by the time it has taken. Let us look at a complete oscillation and we remind ourselves about that particular distance for a complete oscillation. Now let's remind ourselves of the distance covered by the wave in a complete oscillation. And we saw that that distance, if we can have a trace, that distance is 3 centimeters plus another 3 centimeters, which is 6 centimeters, plus another 3, which makes 9 centimeters, and plus the last 3 centimeters, which makes 12 centimeters. That is the distance covered by that particle when it executes one oscillation. So at least in our equation there, I have the first physical quantity, which is distance, which is 12 centimeters, and that distance is called wavelength. Now let's think about the time it takes to make one complete oscillation. And we saw that it was 1.7 seconds, and that one was the periodic time. Those are the physical quantities which I want you to remember when we substitute over here. The first thing that we did is I alerted you that many students make the mistake of using the letter S to represent speed. That is wrong, because you will learn somewhere later on that the letter S is used to represent displacement. And I've used that one in this particular lesson. So V is the symbol that is used for speed, whether you're talking about speed or velocity. Of course, there is a difference between speed and velocity. But at this particular moment, let's just talk about speed. And we just mentioned that its symbol is V. So we consider a complete oscillation. And in a complete oscillation, the distance covered is wavelength, while the time is periodic time. All right? At that particular moment, I want us to pause there and think about the kind of graph which we could draw for displacement distance graph. And we saw that this is the kind of graph that we get. From a displacement distance graph, Of course, at this point, you can see I'm using the symbol S to represent displacement. So don't lose sight of that. So there are two physical quantities we can get from this graph. One, we can get the distance covered by the wave in one complete oscillation, which is referred to as wavelength. And we can also get the amplitude of the wave, which is 3 centimeters. That one is important. And you can see for a complete oscillation, the wavelength is 12 centimeters. There are several ways that I alerted you of how you can measure the wavelength. You can either look at from this point to this point, or from this point to this point, or from a trough to the next trough. The next important type of graph is a displacement time graph. Displacement time graph. The two physical quantities we can get from a displacement time graph is again amplitude. Amplitude can be obtained from both graphs. Amplitude and periodic time. Don't get confused here, because sometimes students get used to this type of graphs and they always think that this one represents time. It's not always time. It depends on the kind of graph which has been given. If it is displacement distance graph, this represents wavelength. But if it is a displacement time graph, this represents periodic time. So we are talking about a complete oscillation, a complete oscillation. So why don't we calculate the speed of the wave when we use the physical quantities obtained for a complete oscillation? What are they? The distance covered, because we require the distance covered in a complete oscillation, is wavelength. The time taken is periodic time. And of course, the symbol used for periodic time is capital T. So the first equation for calculating speed is this one. If the distance given and time is given, don't worry about anything else. Just substitute those values into that equation and you get the answer. Or if the wavelength and time are given, use them. Or I came to this equation here and we agreed that this equation can be written like this. Just like, you see this fraction here? That is the fraction I used. 5 over 7 can be written as 5 multiplied by 1 over 7. You have not changed anything in that fraction. Similarly, lambda over t. By the way, lambda is the symbol that is used to represent wavelength. Wavelength. Lambda is a letter in the Greek alphabet, just like alpha, omega, theta, beta, and so forth. All those are letters in the Greek alphabet, and we use them in physics to represent certain physical quantities. We have already discussed this one before. So, I can split this equation like this. Why I split it like this is because later on I'm going to show you that when I get the inverse of time, I will get the frequency. I will show you in the next lecture. So instead of 1 over t, I can use f, and that is how f comes in here. So 3 equations that are linked to each other. It's just one equation, but it depends on what you are provided in a question if you are required to calculate speed. If distance and time is given, well and good, use them. If lambda and t periodic time is given, use them. If lambda and f, which is frequency, is given, use them. And of course, somewhere I had already mentioned that the SI unit of frequency is hertz or per second. That is a quick recap of what we discussed in that 1.5 hour lecture. So I hope you find this one useful. I'm going to expect you to use this particular video to recap the main points. Write down the main points, and then from there, go back to the Google Classroom and now attempt the assignment for this first part of study of waves. And I wish to see you next time when I teach you the other aspects of waves.